Hi, my name is Akshay and this is Half Sleeves.
In the last video, I told you we would look at the Python code implementation of the condition to converge to correct minimax point. You can find the link to the last video in the description. But I think it is also important to show you the Python implementation of GDA or Gradient Descent Ascent and show you how unreliable is Gradient Descent Ascent to converge to a minimax point. So in this short video, we will implement GDA or Gradient Descent Ascent on some simple examples and see that even on simple loss function examples, GDA gives the wrong minimax point. And then in the next video, we will look at the Python code implementation of the correct method to get to that minimax point. So to start, we will be using Python library AutoGrad to compute the gradients and get to the minimax point. So in line number 1, we will import the function grad from the library AutoGrad. By the way, you can simply pip install the AutoGrad library. Then in line number 2, we will import autograd.numpy as np. Actually, the autograd library needs numpy to do its calculations, but they also need some additional functionality in numpy to calculate the gradients. So they took the original numpy and added some additional classes and functions to it, and then included this new version of numpy in their library. In technical mumbo jumbo, this new numpy is also called a wrapper around the original or the old numpy. So in line number 2, we will import numpy from the library autograd as np. Next, in line 4 and 5, we will define our inputs x and y. Remember, x and y are the output of the generator and the critic. Generator and the critic which have randomly initialized weights. Graphically, x and y represent the points on the loss function where you will start minimizing and maximizing the loss function. So as we progress moving towards the minimax point through gradient descent ascent, the x and y coordinates should change and eventually x and y should reach to the minimax point or very near to the minimax point. In line 8, we define a very simple function called loss underscore function. And this function is exactly what it sounds like. It is a loss function. It takes 3 inputs. First 2 are the x and y, which are the output of the generator and the critic. And the third input is called equation. It's the name of the variable, equation, which would be one of the 3 integers, 0, 1 or 2. There are 3 different loss function equations in the function loss underscore function. And based on the value of the variable equation, the loss function will choose the equation and input the x and y value in that equation and return the value z of the function on that x and y. Next, in line 18, we define a variable called equation and we assign the value 0 to it, which means that our loss function equation would look like the equation in line 10. Next, in line 20, we create a for loop for 300 loops. Now in line 21, we will create the function z underscore x, which calculates the gradient. We will create this function with the help of the function grad, which we imported from the library autograd in line number 1. The function grad takes 2 inputs. The first input is the 2-variable loss function, and the second input is an integer, which indicates the variable with respect to which the gradient is calculated. 0 here indicates that we want the gradient to be calculated with respect to x, and 1 indicates with respect to y. Now, this function grad will output another function z underscore x. We will use this function to get the actual gradient values. In line 23, the function z underscore x will take 2 inputs, x and y, and will give us the gradient of our function loss underscore function with respect to x. Similarly, in line 22 and 24, we can calculate the gradients with respect to y. Now that we have the gradients of our loss function with respect to x and y, we can now find the minimax point by maximizing and minimizing x and y. So in line 26, we minimize x. We take our gradient, multiply it with the learning rate, and subtract it from the original x value. So this new x we get minimizes our loss function in x direction. Similarly, in line 27, we maximize the loss function over y. In line 28, we take the new x and y values obtained in line 26 and 27 and put it in our loss function and get the new z value. Then in line 29, we print the new z, x and y values. Remember, now when the for loop runs again, the x and y values are not the values from the line 4 and 5. They are the new x and y values which were minimized and maximized in the last loop in line 26 and 27. Now our gradient descent ascent algorithm will maximize and minimize x and y and then print it, and it will do it 300 times in a loop. Remember that this GDA code finds the minimax point of the loss function in line number 10, and the correct minimax point of that function is at 0, 0. So let's run this code. The first value printed is the z value, and the next two values are the x and y values. These printed values keep on increasing, but we know that the minimax point is at 0, 0. So clearly, GDA diverges away from the minimax point and does not converge to it. Now in line number 18, let's change the integer to 1 from 0. Which means that we will change our loss function to the 1 in line number 12. And the correct minimax point for this loss function is not at 0, 0. I repeat, the minimax point for this loss function is not at 0, 0. So again, let's run this code. These printed values keep on decreasing and they approach 0, 0. But the minimax point is not at 0, 0. So clearly, GDA converges to the wrong minimax point. Again, now in line number 18, let's change the integer to 2 from 1. Which means that we will change our loss function to the 1 in line number 14, which is much more complex than the previous loss functions. The correct minimax point for this loss function is at 0, 0. So again, let's run this code. These printed values keep on oscillating and don't approach 0, 0. But the minimax point is at 0, 0. So clearly, GDA does not converge to the minimax point. The loss functions in the line 10, 12 and 14 are very simple and only are two variable loss functions. But on the contrary, actual GAN loss functions are functions of at least thousands of variables and are much more complex. So as we saw here, GDA cannot even converge to the minimax point, or it converges to the wrong minimax point for even these simple examples. So how can we expect that GDA will converge to the minimax point for even more complex loss functions? In the next video, we will see the Python code implementation of the correct method for converging to that correct minimax point.